Good afternoon, Professor, and happy
Good,
Halloween.
good afternoon. Thank you. Happy Halloween. Awesome. 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 Good afternoon. Okay. So wait. Oh, excellent. And happy Halloween. Yes. Oh, wow. You guys are totally Halloweening it up. I see. I see. Okay. This is great. This is great. And we're gonna wait. Let's see. Oh, and David is. Wait, is David like literally in the dark for Halloween? Okay. Wait. Okay. So good afternoon. I think that was. I don't even know who actually said the first. I would have said Savannah because I'm just connecting to audio now. So I'm not even sure who that was initially. And Caitlin, it must have been Caitlin because I know Caitlin wins the award. Caitlin's been here since like Columbus Day or Indigenous. I mean, I totally noticed that, Caitlin. Okay, but yes, happy. Okay. Happy Halloween. Especially to Amanda, to Caitlin, to Savannah, to Kevin, to Shamil, to Elda. Well, I mean, obviously to everybody, but I totally see the avatars. I appreciate. I should open up a portal. You definitely get points. Wait, there's more people, or maybe that's maybe that's inappropriate on my part. But okay. And good afternoon. All right. So in the chat, good afternoon, David K. Oh, and there is Carolyn. All right. Good afternoon. Happy Halloween. Good afternoon, Jeff. Get out more people. Okay. Right. See, you guys have the advantage. I mean,
Good afternoon.
Good afternoon. Oh, she said, good afternoon. Awesome. You win. Not that it's a competition. Okay. And not that other people lost. Okay, so good afternoon. Also, David. Good afternoon, Jamalet. Good afternoon, Amy. Good afternoon and happy Halloween, Kevin. Good afternoon, Amanda. Good afternoon, Sophia. Good afternoon and happy Halloween, Caitlin. Good afternoon, Shamil. Good afternoon, David. And I'm wondering about the 11/18. Wait, that's not his birthday. 11/18. I'll have to figure that out. Or maybe it's just like not significant. See, my problem is I think everything is significant. Okay. But that's insignificant. Okay. Good afternoon, Chloe. Good afternoon, Adon. Good afternoon, Savannah. Hi, Christina. Good afternoon, Felicia, who told me something before and I agree with whatever it was, or yes, no problem. Oh, yeah. No problem, bro. Okay. Wait, who else am I forgetting? Christina, Shamil, Amy, Chloe. I think I said hello to everybody. Okay. Yes. Okay. So, okay, last class, but I hope you do have a good, I mean, yeah, I still like Halloween. I mean, what can I tell you? I mean, I'm whatever. I mean, I have kids. But one of my kids is your age, like literally your age, maybe a year younger than some of you. So I don't know what he's doing this year, but my younger kid is 8. So like we totally do this. Okay. And in fact, I don't know what I'm going to do about the other class. Okay. So here's the deal though. A bunch of stuff. Like, okay, so last class, we got so involved in talking about the exam. I kind of apologize for that. I kind of hope at least it made some things clear, maybe that I wanted to say next time or another time. I just posted something in Google Classroom that I do hope you got. And let me be really clear again, if I can ever be. I mean, I'm no stranger to personal stress or academic stress. I've spent many years of my life feeling it. I've spent an equal number of years of my life trying to fight it or find a cure to it. But by it, I mean to stress. I consider a major part of my job these days trying to find ways to learn and advance and do well in life with a minimum of stress. That means for me and for you. One quick side note of that. Intensity, I'm all for. I'm an intense guy. You are intense people. Otherwise, you wouldn't have come this far in academics and in science. You're sacrificing a lot for all of this. But I have come to learn at various points in my life, intensity and stress are not the same thing. Like it's not automatic. And some of you already know this. Some of you were born knowing this. Some of you don't need to hear this. But it's not. One doesn't have to be stressed in order to be intense. Stressed is like the unhealthy, like unenjoyable version of intensity, right? I mean, anyway, why am I saying all this? Because we do have an exam coming up. I did just put a bunch of information in Google Classroom that hopefully you got, or maybe you can confirm or deny in the chat where it was just an announcement. It's called Expectations Re-Midterm Exam. It's just to lay out in concrete terms what we basically said, maybe spent too much time saying last class. I'll repeat the basic info maybe in a moment, but just so you know, again, you're going to get more information about it. You're going to get a practice test posted. Well, so again, the bottom line is that for the class, the exam will be the actual midterm exam will be posted a week from this Thursday. It'll be due back in class, due back right before class the following Monday. All of this is now written, hopefully clearly in Google Classroom. If you have questions, you can text me or email me. So you'll get a practice exam like posted this Thursday. It's not due to me. It's totally for practice, but it is the way to practice. It is the way to study. Far more important than going back to a textbook or anything like that, whatever. It's the way to study for this exam is to practice for it with the practice exam and to believe and trust that the practice exam will be darn close to the real exam. So your go-to is the practice exam. Ideally, what you do, ideally, you take the practice exam 3 times before you take the real exam. And that means, well, we'll get into all that, but ideally. But that's even though the real exam is open book and all of that. The practice exam will be darn close to the real exam. The details of how close will be are in the posting. Anyway, all I'm trying to say is the more information I give you about the exam, no, it has not yet. An announcement about expectations and guidelines and so forth about the exam has been posted about 10 minutes ago. The practice exam has not been posted. It will be posted no later than this Thursday, 8 p.m. So then you have all weekend to do it. That's the way you should study, is just try to do the practice. See what you can do without looking, see what you can't do without looking, et cetera. It says, see what you have to look up in order to do it with your friends, blah, blah, blah. And then next week you come to class Monday and Wednesday with questions about it. Maybe primarily and I'm not saying I'm going to spend the whole period Monday and Wednesday on questions on it, but I'll spend a lot, and particularly Wednesday. Okay, so it'll be posted this Thursday. That's what you do this weekend. You drop everything else. Like, don't try to whatever you think you're behind on, or whatever you think you never really learned or something. You don't you learn that through the practice exam. You do what people sometimes consider cheating, but isn't. You work backwards. You use the practice exam to see what you know and what you don't know, and you go back and figure out the things that you don't know from the practice exam. Don't I think you get what I'm saying. So it'll be posted this Thursday to answer direct chat person's question. And any more information that I give, or any more things I say about the exam, which will be a lot, or any stress that you ever hear in my voice, is because I find these things stressful, and I'm trying to do everything I can to make it less stressful, including that I shouldn't project my stress on you. I promise you that anything that is stressful about any of this is by nature, not by my design. I think things are stressful enough by accident that my goal in this point in my life is to put every intention I can into reducing stress. I'm not trying to increase it for you or for me. Now, obviously I can't eliminate it, but anyway, so the only thing that's the things that are tricky about the exam and so forth are whatever is tricky in my view about physics and nature and life in and of itself. I'm not trying to add layers of trick to that anyway, or treats for that matter. Now, I just already said, because we spent but from here on in, the information is basically written. You text me or email me with personal questions about it or whatever, or personal issues. But the real way to prepare for this exam is, once you see the practice on Thursday, do that, and then come in with questions about that Monday and Wednesday. Again, definitely work together. Again, even on the actual exam, you can. And then the final analysis, what you want to reflect on the final exam, on the final copy of the actual exam, is your is your original, not your original, is your comprehensive, thorough, personal version of the solutions by the time you get to them and you write them down. The bottom line litmus test of this whole thing is when you finally submit a final copy, I don't care how much information you got at the last minute. I don't care how much information you got from your friend. The more, the better, honestly. I don't care how much information you got from Khan Academy or whatever. But by the time you write anything down, you picture yourself sitting in my office with me and me asking you questions about what you wrote down and saying, okay, but where did this come from? Like, why is this true? Okay, what about this step? What's this true? And if you can confidently in your heart picture that you could, and this happens, not to everybody, I'm not saying it's part, but I will do it with people that I have issues or questions or suspicions or concerns about. You picture picture yourself in a Zoom with me, whatever. Picture yourself defending vocally everything you wrote down. And if you can do that, if you know in your heart of hearts that you get what you wrote down, then we're good. And if not, not. Okay, enough of that. So what I want to get back to now in a moment, and again, pepper me with questions throughout this class about the exam procedure, whatever, but hopefully, or maybe someone could just confirm or deny in the chat. Did you see the sheet that just went up that sort of said it's called expectation? Yeah, great, awesome, thank you, awesome, thank you, I love you all, happy Halloween, you're getting treats, not tricks, and you're getting falsetto fun. Thank you, awesome. All right, so great. So thank you, Amanda, thank you, Caitlin, thank you, Felicia, thank you, Caroline, thank you, Amy, thank you, Kevin, thank you, Nicholas, thank you, Amy. Oh my God, there's also two. What? No, I've done this before. Okay. Okay. So now what we're going to do, and just to be clear too, one of the reasons it hasn't been posted yet is like, even though I'm trying to be, we do have to cover material in this class and we get faster and faster, as I mentioned, and through Physics 204. So anything is fair game. You'll know, as far as what does the exam cover, you'll really know once you get this practice exam. But the practice exam covers everything through, like we're still going with material, like we haven't stopped with material. So I want to get back in a moment to the thing that you were all going to do in breakout rooms last Wednesday. You didn't get a chance to because we talked about the exam the whole time and we got your input about it. So now I'm just going to go over it. I'm going to remind you of the problem and go over it. And this is now part of two-dimensional kinematics. What it's really about, the problem that we started last Wednesday was about how to add vectors. Well, yeah, how to add vectors. Specifically, it was about how to add displacement vectors. Remember, a vector quantity is any quantity with magnitude and direction. So velocity is a vector, acceleration is a vector. Ultimately, you're going to see force is a vector. So the procedure that you're learning now happens to be an example of two displacement vectors. But if we understand this procedure, specifically this procedure called adding vectors by components, then this procedure will work for all kind of vectors, including very specifically velocity vectors, where the meaning of what we're doing will be less obvious or less intuitive than the meaning of what we're doing with displacement vectors, but the mathematical procedure will be the same. So this is a once for all, one size fits all mathematical procedure that we're looking at now for how to add two vectors by what's known as the component method. It deploys forms 4 and 5 of Galileo's principle of relativity. It's all about deploying, everything in physics is about deploying Galileo's principle of relativity in one form or another. And it also deploys, I wrote sine squared theta plus cosine squared theta equals 1 down there in the sheet. That's my catch-all way. Whenever I write that, just so you know, I mean, you might remember that as a trig identity. I mean, it is a trig identity, like it's always true. But, you know, I write that sine squared theta plus, and you may want to make a note of this in your notes. Whenever I say sine squared theta plus cosine squared theta equals 1, that's a catch-all way of saying that everything that I don't know if you remember this from math or if you recognize it, but what that really is, sine squared theta plus cosine squared theta equals 1, what that really is a way of expressing the Pythagorean theorem, but expressing it in terms of theta and trigonometric functions. That is, well, I don't want to get into if you really think it through, it's really like saying a squared plus b squared equals c squared, it's in a unit. If your right triangle was drawn in the unit circle, if you had a hypotenuse of 1, if you had a radius of 1, and then you added the opposite side squared plus the adjacent side squared. If you think about it, so put it another way, multiply both sides of that equation by a hypotenuse, and you'll see what I'm saying. That is a catch-all way. Whenever I write that, what I'm trying to say is that means to me that Pythagorean theorem applies and SOHCAHTOA, all your sine, cosine, and adjacent, sine, cosine, and tangent definitions, relations for right triangles apply. When I write sine squared theta plus cosine squared theta equals 1, it means everything we know, all the basics that we know about trig as applied to a right triangle applies. So what I'm really saying is, how do we add vectors by the component method? What we do is we recognize that every two-dimensional problem is really two one-dimensional problems occurring independently yet simultaneously. So what we do, and I'm about to turn the page, I'm about to get to the problem that we did last time. I'm just summarizing again as always, because this is part of the exam. This, for what it's worth, like, this is fair game. What we do whenever we add two-dimensional or three-dimensional or four-dimensional vectors together is we say each one of these two-dimensional vectors is really two one-dimensional vectors occurring simultaneously yet independently. So so we take what we do to add vectors by the component method is we treat every single vector we have as a hypotenuse of its own little mini triangle, for which the two perpendicular legs are legs that lie along the x-axis and the y-axis. We divide every two-dimensional quantity into an x piece and a y piece, and then we independently add up all the x pieces and we independently add up all the y pieces and then put them back together, exactly as you did in lab 3, whether you thought about it consciously that way or not. And the whole idea of lab 3 was to get you to see that you do this, that it's a natural thing to do, even unconsciously. So now we're just consciously, like we always do in physics, we're just consciously putting a script to it. So, okay, enough of it. Okay, so we're adding two-dimensional displacement vectors by the component method. That was the purpose of the problem that I assigned last time, but we never really got to do. So I'm going to go over right now. So what was the problem? Again, it's an example. It's a displacement example. The example was you walk 5 meters at 30 degrees northeast. Right? So there's my little picture, 5 meters, 30 degrees northeast. Then you walk 8 meters at 60 degrees southeast. So there's a little picture of that. And the question was, from the initial position to the final position, what is your total displacement? Right? That was the question. So we're literally saying, given two two-dimensional displacement vectors, what is the total two-dimensional displacement? That's what we're asking. And let me remind you, if we're asking for displacement, we're asking for a final answer that has magnitude and direction, a final answer that can be, but now we're in 2 dimensions. So magnitude means size, always. Direction means angle and points of the compass, right? That's what like direction now means to us, is now that we're in 2 dimensions of space. And so when we're asking for a final displacement vector, we are asking for a final arrow whose length represents its magnitude and whose tip-tail orientation, angle, represents its direction. That's what we're looking for. Our answer won't be complete unless it has those 2 pieces of information. So what do we do? Okay, here we go. A lot of build-up. What's that? 12 minutes? Okay, so 15 minutes of it, 20 minutes of build-up. Okay, so here we go. And again, this is in principle what I don't think you ever got it. Well, I'm just going to show you. I guess you didn't really get a chance to work on it, I think. So, and this is not a homework problem for people who are just tuning in now. This is a problem that I just presented in the Zoom last Wednesday, and it's in the notes. And now it's in the class notes and all that. But here's now the solution. Even if you didn't get it, here's how you do it. Yeah, it's a little unfortunate. Well, all right. So first of all, this picture at the top of the page. This picture is a representation, a diagram, a picture of what's going on in the problem. Like if this problem were an exam problem, this would be step 1, like diagram fact pattern, right? in this step that I'm doing at the top of the page here, at the top of the page, hang on, just to be super clear about this. Like this, that is a diagram of what's going on. That is not a solution. So what's going on is first I walked 5 meters at 30 degrees to the northeast, right? Then from the end of my first walk, I walked 8 meters. Did I even write it? Sorry. I then walked 8 meters at 60 degrees to the southeast. And I want to know overall how I walked, like from the beginning of this whole process to the end, where I got to. Now, a couple of things about this. First of all, notice that I drew, so I'm drawing the situation. I'm drawing the situation, the question itself. So notice I took the two black vectors that I'm adding together and I placed them tip to tail. Now, I think that's very natural. If we're just asked if this is displacement, it's very natural, like you would do it without me, and you did in lab 3 without anybody having to tell you, because if you walk some way and then you walk another way, of course, like you start your second walk from where you ended your first walk. So if each walk is represented by an arrow, of course you would play, I think it's of course you would place them tip to tail. What I want to say right now though is that this procedure, it can be universalized. It should be generalized. Like whenever we're going to add two vector quantities, even when the meaning is more abstract than just walking around the world, whenever we're going to add two vectors to get a total displacement vector, we're going to place them tip to tail. And we're going to say that the answer, the total, the sum of these two vectors is some vector that would be drawn from the original tail of the first all the way to the final tip of the last. Okay, like so the red vector in this picture represents our answer. Whatever its length is will be the length of our answer, and whatever its angle is will be the direction of our answer. If this diagram were drawn perfectly or like super well to scale, like if I literally used a ruler and a protractor and I kept everything kind of like in lab 3, if I kept everything to scale, then it'd be, we could rely on this picture to actually do the computation for us. We could. If I drew it that carefully, then the red answer like would be the answer. If I just measured it with a compass and a protractor, I could depend on that being my answer, which goes to show you that these vectors, they're not just raw. Right now, I'm kind of making a rough sketch, but vectors themselves are computational tools. Like if we use them properly, they reveal numerical answers of great precision. Now, I didn't draw this picture perfectly to scale. So it's a sketch of what's going on. It's helping me picture the process. It's giving me a sense, for example, that when I get my final answer, it should be a number that I think is going to be longer than 5, probably even longer than 8, right? But I don't think it's going to be 13. Like my final displacement, I don't think is going to be 5 plus 8, 13. I didn't walk that far. Why? Because I didn't walk everything in a straight line. Like I bent at angles. That's the difficulty that we're taking into account here, is the funky directions. So if I walk 5 and then I walk 8, that only makes a total of 13 if literally the 5 and the 8 were parallel with each other, if you see what I'm saying. So my final answer is going to be something greater than 5, something greater than 8, but I don't think something as great as 13. That's number 1. Number 2, the angle now, I think this diagram is off scale enough that I don't even think, I think the answer makes it look like it's going to be pointing to the south east. And is that, does that turn up here? Hold on. I think that's right. 1 second. Yeah, sorry. Yeah. So the answer makes it look like, I mean, my picture makes it look like my answer should be like to the southeast. So it's a good indication. If by the time I get to my answer, if I get something that's like way lower than 5 or greater than 13, and its direction is like in the northwest, that means I have to double check something. Like either my answer is wrong or my original picture, like, but I have to, if this were an exam, I'm using this as a pre-check on the kind of answer I should expect. All right. Okay, what's the takeaway of this? Well, the takeaway is what's written in the box. From now on, placing vectors tip to tail represents adding the vectors all time. And literally that means, and I got to say this again, because we're about to do it in the problem. We're going to do this funky thing where we're going to add by adding, if you'll see what I mean. I just want to make clear that like, when I say placing two vectors tip to tail means adding them, it means you place two vectors tip to tail, and then the answer is the vector, that completes the triangle that goes from the original tail to the final tip. So similarly, then, any two vectors, you might want to write this in your notes. If you buy what I'm saying, or if you see what I'm saying, that placing vectors is the representational graphical way, placing vector arrows tip to tail is the way of adding vector quantities, whatever the vectors represent, then similarly, placing two vectors tail to tail or tip to tip means subtracting them. Like if you look at my picture here, the red vector minus one of the black vectors equals the other black vector. Like that does follow from what I'm saying. And so from here on in, whenever we do any vector problem, it's not good enough just to draw lines and triangles. Oh, so cool. I love when he does it just, okay. He does it just frequently enough to be awesome and just infrequently enough to be awesome. I mean, if he did it every minute, like we'd all drive us all crazy, right? But like he does it just enough that I believe him every single time. And also Amy is okay. Anyway, okay. You both. I should have brought virtual candy. Wait, do they have a virtual candy emoji? Hold on. Wait, let me just see. I should get candy. Oh, I don't think I have candy. Okay, that's as close as that's treat. Okay. Can you imagine how creeped out you'd be if you ever did come to my house? Oh my God. I'm that guy. I know. I'd give you like a calculator. Okay. Okay, I'm so distracted. See, they didn't have ADHD when they had it, but they did. Okay. Okay, so understandable, makes sense. Right, cool. So if there's a takeaway for taking an exam, the takeaway is we're going to use a lot of right triangle information now, or I'm going to. Yes, I'm going to rely on triangle information that you have from your math classes, and I don't think will bother most of you. But remember, this is physics, not math. So you're going to use these triangles to do. Oh wait, okay, hold on. There's something in the direct chat. One second. Oh, okay. To clarify, I'm not going to read the name because this isn't direct chat, but it's a great question. And so the answer is equal subtraction. All right. So someone just said in the direct chat, just to clarify, tip to tail equals addition of vector quantities. Yes. And tip to tip or tail to tail equals, we should say, subtraction of vector quantities. So if that was a typo, no big deal. I'm not trying to correct you, direct chat, but yes. So tip to tail means adding, and tail to tail or tip to tip means subtracting. Yes. And that's like a really big point. It becomes really important to everybody, especially with velocity problems, which cool, awesome. And all of you in direct chat participation, treat. Like where this is all going, like the last thing we're going to do before the actual exam is we're going to have to apply this method to velocity vectors. And I'm saying right now, like warning, foreshadow, whatever, the math that we're about to do is exactly the same math for adding or subtracting velocity vectors. But the hook with velocity, but velocity vectors are a tiny bit harder. That's where we do displacement vectors first. Why are the velocity vectors a tiny bit harder? The math is exactly the same. But with velocity vectors, you have to actually understand what it means physically well enough to know whether to set up your problem as addition or subtraction. That's a foreshadow, but that's why I'm making a big deal of this right now. Like if to the extent that your job in physics is like to translate my words into, or anybody's words into mathematical computation with velocities, we give you words and then you have to actually understand how velocities work well enough to know to set your vectors up for subtraction or addition. You'll see that. That's a foreshadow. You'll see that. But so yes, what person just put in direct chat, totally awesome. And yes, you want to know when you add two things, you're tip-tailing them. And when you tip or tail them, they're subtracting. And then hopefully that's clear in this diagram right here, boxed in yellow. Like red minus black equals black. Black plus black equals red. And it's easiest to picture when you picture walking. Like, and stop me if you don't, but the direct chat person, that was great. Okay, I'm going to stop saying. Okay, so that's the picture. That's like step one DFP of what's going on with these two vectors. Now, our goal is to add them together to get a total displacement vector that's going to look somewhat like that red arrow. What do? What we do is we invoke GPR5, We invoke the idea that every two-dimensional problem is really two one-dimensional problems existing independently yet simultaneously. So what we do is we're going to zoom in now. What's happening on the bottom of the page underneath the yellow box, we're zooming in on each vector individually. And we're going to say that each vector is its own hypotenuse of its own right triangle. Like, we're going to use right triangle knowledge now because the x-axis of life and the y-axis of life are necessarily at right angles to each other. We're going to invoke our knowledge of right triangles, and we always will when we deal with vectors by component methods. We always will, but also warning, I should stop with these warnings, but also warning, we always will and we always can, not because the vectors themselves fall into some kind of right triangle. They don't necessarily, and they don't here. Like, even though 30 plus 60 sounds like it makes 90 or something, notice those two black vectors that we're adding together, they don't together, they don't make a right triangle with each other. I'm saying each one, when we zoom in, we're going to make it its own right triangle. And sorry, that just reminded me of one other caution. I should really stop with all the cautions, but it is Halloween, so be cautious. And please, if you get a full-size candy bar, then A, report to me, and B, share. No, here's my other caution, quick caution. Sorry for all the sidebars. Is that, notice in my picture, in the yellow square, in my picture, notice that second vector when I said it's 60 degrees to the southeast. And I remember even I had drawn it wrong originally, and one of you corrected me. It might have been David, or it might have been Nicholas. Someone correct, but then a bunch of other people noticed it too, and sorry. But notice that second vector, its direction is 60 degrees south of east. Notice that means, as it always will mean, it means that vector's own direction in and of itself is 8 points, 60 degrees south of the imaginary eastern horizon, the eastern reference line. Like, what I'm saying is, notice that the second direct vector is not making a 60-degree angle with the first vector. That's not the point, right? Each vector has its own direction and magnitude, and then we put them together. We don't, right? Each one has its own direction and magnitude, and then we put them together accordingly. The angles are not there's no guarantee that when you put these vectors together, you're going to get some special shape that has some special knowledge that you know from trig. Nuh-uh. What I'm saying is, in order to add them, we zoom in. So here we go. Finally, what time is it? It's probably like 1:40,000 o'clock. Okay, it's 12:50. Okay, we zoom in on the first vector. The first vector. So I'm zooming in with the blue dream sequence. The first vector is 5 meters to 30 degrees to the northeast. So what I say to myself is, oh, remember when I place two vectors tip to tail, I add them. So I say, oh, you know what? I'm a New York City guy. I was a Manhattan guy. I know that when I go northeast, that's actually equivalent to going somewhat east and somewhat north, independently but simultaneously, right? In other words, the vector 5 diagonally is actually equal to the sum of some pure eastern vector, tail to tip, and then from its tip, the tail of some pure northern director. Northeast actually equals north plus east, or even better, it equals east plus north. I'll get to that technicality in a moment. But, right, so I take that northeastern vector and I say it's actually itself the sum of two smaller constituent components, a pure eastern one and a pure northern one. I'm dividing it into the two jobs that it's doing individually, independently, along the independent axes of space. And you might say, why? Because I have all the equations and all the knowledge and all the physics I need for each individual axis of space. So I'm bringing the physics back to what I already know, which is what happens in a number line. This number line is no different from this number line. They're each just a number line. So I say 5 to the northeast is actually equivalent to some amount east plus some amount north. Similarly, then I zoom in on the other one, and say 8 meters to the southeast is actually equivalent to some amount east plus some amount south. Now, I'm going to Is this the right time? And now I'm going to get the number. Yeah. So let me go on. I'll explain the awkwardness of east, south, southeast in a moment. But that's what, so copy those triangles down. So then I invoke my good old now. So now I have right triangles, and I always will in all vector problems. Again, each vector, and this process I'm doing for adding two vectors. Once you understand the process I'm doing, you could add as many vectors as you want. I mean, 3, 4, 5, 7. I mean, it's a reiterative process. I'm saying that every single vector itself can be viewed as its own hypotenuse of its own little right triangle and should be viewed that way. So I took this 5-meter vector and I divided it into an eastern component and a pure eastern component and a pure northern component. Then I use SOHCAHTOA and I say, okay, the eastern component is adjacent to the 30-degree angle. The northern component is opposite to that 30-degree angle. And the right angle is the angle formed between the y-axis and the x-axis, right? So I have, and the 5 is the hypotenuse. So I have a clear right triangle here. And just side note, like you notice the angle, if I do everything properly and consistently, like it's all about consistency. There's other choices that could have been made. And I'll get to that. I know that for some of you, SOHCAHTOA sort of makes sense, but some of you might be like the way I was at one point where you might always be thinking, I kind of always get SOHCAHTOA when it's set up for me, but I kind of never know which is the angle. Like, how do they know which is the angle? Like, once I know, then like, okay, what? Like you might have noticed that, you know, whatever is the opposite side means opposite to the angle. But if you pick the other angle, then the other side is opposite to that. I don't know if that's ever, if you're not confused by that, good, keep on going. But if you've ever been slightly confused by that, or you knew you were confused by something and you didn't know what it was, and maybe it was that, bear with me. I can clarify that further and I'm with you. But the first thing I'm going to say is what we always try to do. When in doubt, we're trying to measure all of our angles from the horizontal. To keep things consistent and clear, one big trick, if you're ever confused about what's the angle or what should we do here, we always try to keep our angles measured from the horizontal because then our points of the compass make sense. Like if the angle is measured above or below the horizontal, then what we're talking about is how far north or south of east or of west something is. If you measure from the horizontal, then all of your compass directionals are like northeast, southeast, southwest. Whereas if you measure from the vertical, then what you're really talking about is how far west of south something is. So then everything becomes west-south or east-north, which is fine, but is more awkward and not generally consistent with anybody else in life. So when in doubt, try to measure your angles from the horizontal for what it's worth and try to set things up so that angles are measured from the horizontal. So then, okay, adjacent means the horizontal leg, opposite means the vertical leg. So, you know, well, so I've written out, so cosine equals adjacent over hypotenuse. Therefore, adjacent equals hypotenuse times cosine. So therefore, the adjacent is like about 4.3 in length. And I did the same thing vertically with the sine. The vertical is about 2.5. Pause here. So in math class, when you use SOHCAHTOA, you're generally using SOHCAHTOA. Generally, you use SOHCAHTOA. Well, often you use SOHCAHTOA when you have the sides and you're looking for the angle or something like that. Here, we generally have the angle and we're looking for the sides. So for whatever it's worth, you're going to see, I'm going to do this over and over for the rest of physics. I always just, from here on in, I think of the adjacent side as hypotenuse times cosine. And I think of the opposite side from here on in physics. I think of the opposite side in any right triangle as the hypotenuse times the sine of the angle, right? And the first thing I'm always trying to do is get the opposite side and the adjacent side of a right triangle. What have I done when I've just gotten these numbers 4.3 and 2.5? What I'm really saying here is if you walk 5 meters to 30 degrees to the northeast, what you've really done is the equivalent. You'll get to the same place as somebody. Look, if you wanted to walk 5, well, yeah, if you want to walk like 5 blocks, it doesn't work. The point is, if you walk 5 meters at that angle, you'll get to the same place as someone who literally walks 4.3 meters directly across town east and then walks 2.5 meters directly north, directly uptown. I'm saying that to go 5 at 30 degrees northeast is equivalent in every way to going 4.3 east and then going 2.5 north, or going 2.5 north and then going 4.3 east, or even better yet, literally somehow going 4.3 east at the same time as you went 2.5 north. That's what it means to go 5 meters at 30 degrees northeast. That's what we're saying. When we find these two components, we're finding another way to put it, you might know from high school, or you might have seen in movies or some weird movies somewhere, is like if yeah, like if I had a pole, or like a long meter stick or something like that, like about a 5 meter stick pointing at some weird angle, and then I shined a light on it, the shadow that it would cast on the x-axis would be 4.3 meters long. And if I shine a light over here, like over behind it, then the shadow it would cast up and down on a wall that was pointing vertically would be 2.5 meters. 2.5 and 4.3 are the vertical and horizontal components, portions, projections, you might say, of this hypotenuse onto the two constituent X and Y axes. There's other ways to say it, but hopefully that makes some sense. Okay, anyway, so we've divided that two-dimensional quantity into its two one-dimensional constituent pieces. Now I do the same thing to the other quantity. The other quantity was 8 meters at a 60 degrees to the southeast. So I say to go southeast is really to go some amount east and then some amount south, right? So I do the same math. The adjacent side of that triangle is hypotenuse times cosine of the angle, which equals, in this case, 4. And the opposite is the hypotenuse times the sine of the angle, which equals 6.9, right? And now the reason I did all that is, again, this all goes back to lab 3, really, which, I mean, correct me if I'm wrong, but lab 3, the graph paper, like Escape from Survivor Island or whatever. This is just the formal way of doing what I think intuitively a lot of you understood, which is that to go like this and then to go like that is really I'm making an XY chart now to accumulate, to just keep a running tally of everything I did in the x-axis and then everything I did in the y-axis. And I'm noticing, or I'm first noting or declaring or deciding that that along each axis is independent, so it has its own coordinate system. It has its own plus and minus assigned to it. North is plus, south is minus, independently but simultaneously. East is plus, and west is minus. So what's the total accumulation of what I've done? Well, first I went 4.3 to the east, then I went 4 to the east. That's in the x-axis. In the y-axis, first I went 2.5 to the north, but then I went 6.9 to the south. Like, if I'm really not just drawing random triangles, but if I'm really keeping track of the vectors with tips and tails and directions, which is really the purpose of all of this, is to actually track direction, then I notice there's a minus sign on the 6.9, like, because I went south. That second triangle took me south, right? So I'm going to add all these up in a minute in the next page. Well, yeah, all right. So I'm going to add them up in the next page. So I just recopied at the top. So there it is. So the total, right? So, and again, this process, I divide each vector into two independent component axes, worlds, coordinates, and then I get the total, like I'm adding up. If I were subtracting vectors, I would subtract these numbers, but I'm adding these vectors. So I add up the numbers, I get the totals. So now I have a total. What I'm saying is, in total, this whole process took me 8.3 meters in the eastern direction along the x-axis, and it took me 4.4 meters in the southern direction, along the y-axis. So now I put those two facts together with one big triangle, right? Like, I create a final right Pythagorean triangle with my results. I say my results are that I went 8.3 to the east. So I draw a big horizontal arrow with a tip at the end, and then from that tip, I put a tail, and I say that I'm going, so this is equivalent to going 8.3 and then going 4.4. That's what this is equivalent to. And so the answer to this big right triangle, the dotted line that goes from the original tail to the final tip, that's my answer to the whole thing, to the whole displacement. So what do? Well, I use Pythagorean theorem to get the distance, right? And I say, and of course now everything's gonna have squiggly equal signs, because I'm like making things up, or like not because I'm not sure, but because I'm doing square roots and stuff now. So I'm going to start chopping off digits from the, I'm just leaving things to like 3 significant digits because that's all I had to begin with. So it's approximately 9.3 meters is my total distance. Notice it's greater than 8, it's greater than 5, but it's less than 13. And I think that makes sense if you look at my original picture and if you think about it. So I ended up walking an equivalent of 9.39, or I ended up walking, like where I ended up was like 9.39 meters away from where I started. And I ended up walking in a certain direction, which I'm saying here to the side. My final direction, which is as much important as part of the answer as the 9.39, maybe it's even more important because I wouldn't be going through all of this work if I didn't care about direction. My final answer is that I ended up going about 27.9 degrees, a little bit less than 30 degrees southeast. Where did I get that? Well, in this big right triangle, I used SOHCAHTOA again, right? I said, I'm right here right now. I said the tangent of the angle equals opposite over adjacent. Now I could use I could use sine over cosine. I mean, I could say sine is opposite over hypotenuse, or cosine is adjacent over hypotenuse. You could do any that works. They'll all get essentially the same answer. I usually use tangent at this point because just in case I did the Pythagorean theorem wrong, then I'm not going to, then that error won't compound. I mean, it's just a taste thing. Plus, I'm just showing myself that I favor my Y answer and my X answer sort of with equal weight. Like I trust my 4.4 and I trust my 8.3 to the exact same extent. So I say the tangent of the angle equals the opposite over the adjacent. Notice I don't put in minus signs here or anything like that. I'm just getting an acute angle. Like the tangent of the angle is like I can see direction from my pictures. My direction is clear in my tips and tails. So I just write the tangent of the angle equals 4.4 over 8.3. That's a 0.3. And therefore, if tangent of the angle equals 4.4 over 8.3, then the angle equals the inverse tangent, right? Or the arc tangent, or if you're doing this on the calculator, which you would have to, tangent to the -1. Now, right now in this stage of physics or in this stage of life, I'm looking for angles in degrees. I mean, for no other reason than that's how I presented the angles. I said 30 degrees to the northeast or 60 degrees to the, so that's the kind of answer I'm looking for. So my calculator should be in degree mode. To be honest, we're soon going to move to the point where everything is radians, but right now the question was presented in degrees, so the calculator should be in degree mode. So I do 4.4 over 8.3 on the calculator and then say second tangent or tangent to the -1 or however your calculator works. And I get that theta equals 27.9 approximately degrees. And how do I know southeast? I know southeast because of my picture. The picture makes it clear that that angle is south of east. And how does that picture make that clear? Because the 4.4 is going down or going to the south. How do I know that? Because of the negative sign in the chart. So you're always keeping track of negative signs. They're very important, but you keep a track of negative signs one axis at a time. Like the negative or positives apply independently to the axes, and they tell you in what direction to put your tips and tails. So, okay, so my final answer to this whole problem, I'm just looking at the time. Okay, my final answer to the whole problem is my total. Sorry, that's not what I meant to do. Sorry. Okay, so this is our answer, our final answer. Again, it's approximate because we chopped off digits and stuff like that, but it's like approximately 9.39 meters at 27.9 degrees southeast. I think that answer makes sense, and I think it's consistent with our original picture, but I also think it's not guessable. Just please notice, like, this is a process. I mean, maybe if I drew my original picture well enough and I measured it, I could get this answer. But other than that, it's not like I could eyeball 5 and 13 and 30 degrees and come up with these. Like, I couldn't look at 5 or what was it? I mean, 5 and 8 and 30 degrees and 60 degrees and eyeball them and go like, oh yeah, the answer's going to be around 9.39, 27 degrees southeast. No, I would know roughly from my picture, but these are very exact numbers. The only way I can get them, well, it is by a kind of method. This is the method we do, component method. I'm going to say one last thing about this, and then I'm going to pause and answer questions. But hopefully this is somewhat. But again, this process, and hopefully as usual, maybe I'm over talking it. Maybe it's very clear. Hopefully we'll see in a minute. But if you get what I'm saying, then this works for any number of vectors in any number of dimensions and any type of vectors. This is literally like what I just taught you, oddly enough, is addition. Like literally what we just did was how to add, which of course you all know how to add numbers. You know how to add 3 + 4 is 7 or whatever. In effect, what you all know how to do already before this is add numbers on a number line. Even when there's negatives, you know how to do it. You know that 3 + -1 means like stand at the 3 and go backwards 1 and you'll get +2. And I'm not condescending when I say that. We all know how to add numbers on a number line. This is a process for taking that knowledge and adding directional quantities in more than one number line at the same time. This is how to add directional quantities in space. This is how to add vectors. It's all based on how adding numbers on a number line and based on the idea that anything in space is really the sum of independent yet simultaneous number lines. Vectors are a trick or technique for combining those two recognitions, how physics works in a number line and how different number lines can act independently yet simultaneously. That's what addition of vectors by the component method is. That's what we just did. If you get it in this hopefully somewhat intuitive example, then it's the same process for any number of vectors of any type in any type of dimensions. Okay, just to make that clear. So it's a big thing. That's adding vectors is what we just did. And it's also subtracting vectors because you just do subtraction rather than addition. One last thing about this. Now that well, actually, yeah, wait, let me pause for a second. I mean, we're not going to do anything else new today. I just want to make sure this is clear, especially since you didn't get a chance to work on it. Are there any questions about this at all? Okay, that's cool. Oh, Caroline picture. Oh, nice picture. Can I just ask this? That's fine. I mean, maybe can I just say, does that mean if you, and I'm not, this is not an example, obviously, I'm just explaining, but just to make sure, can I get an electronic thumbs up if you are still with me? If you think, okay, cool. Awesome. Thank you, Caroline. Thank you, Savannah. Thank you, Caroline. Thank you, Caitlin. Thank you, Sophia. Thank you, Kevin. Thank you, Christine. Thank you, Felicia. Thank you, Amy. Thank you, Amanda. Did I say that? Caitlin. Thank you. Awesome. Thank you, Amy. Did I say that? Thank you, Jamalot. Okay, cool. All right. So I'll assume you're cool. All right. One more little detail. I mean, because I'll also, this is one of those, just warning. I feel like adding vectors by the component method. For me, it was one of those things that even And look, I got confused watching physics more easily than some of you, I think, honestly. Like I've done it many, many times at this point, but I'm never being falsely modest or trying to BS you. And believe me, I found physics confusing and stressful many times as a student. I kept choosing to do more because I thought it was really cool, but that does not mean I thought it was easy. So what am I trying to say? That this, and some things I knew even when they were being presented, like when integrals were being presented to me, I had no idea what the professor was talking about, and I knew I had no idea what like it went way too fast. It was way too abstract. The first time I heard about integrals, I had no idea what they were saying, and I knew I had no idea. I even probably got to the point of deciding I didn't care or getting angry or something like that for a while before it got straightened out. But with this, when this was presented to me in some kind of way or another, I did think I knew what was going on. I was like, oh, that makes sense. That makes sense. That makes sense. But what I didn't realize, I just want to warn you right now, is this is something that does take practice. It looks really clear when someone's doing it, maybe to some of you, but there's actually a bunch of choices I just made while I was doing it that might not really look like choices. They just look like straightforward, and you don't realize they're well, one, I didn't realize that there were choices until like I had to sit down and do this myself, and then realized there was choices to be made, and I often made the wrong choices. And so here's what I want to, so let me show you one at the risk of confusing you further. But well, really what I'm trying to say is you got to practice this. You really have to practice on your own to make sure you got it right. And so a lot of that last homework assignment, the most recent one, eventually becomes practice in this, whether it's displacements or velocities or whatever. But okay, so I'm just saying, I'm going to take one more pit. Okay, just so you know, so I'm saying the whole idea, the whole method is you take every vector that you have and you split it into its own components, and then you tally up all those components in an XY chart. You get the answers, and then you put that back into one big triangle. So you break every vector into its components. You add up all the components, you get a final X component and a final Y component. You make a final triangle, and then you see what the hypotenuse is of that final triangle, and that's your answer. So we literally are taking a bunch of arrows, breaking them up into smaller arrows, adding up all the smaller arrows, getting big arrow, and then putting that back together. It's definitely a deconstruction, reconstruction process. And it'll almost seem circular until you understand that the whole reason we're doing it is because we can deal with one dimension at a time. But the only way we deal with two dimensions simultaneously is just that. We deal with one dimension at a time. What I'm getting at is you got the part where we split the vectors into their own components. Be careful with that. So notice this. When we had 5 meters at 30 degrees to the northeast, what I'm saying, this is the part that seems really self-evident if I just do it, sorry. Oh my God, no way. Wait. I'm looking at direct chat. Oh, what a nice thing. Okay, I'm not going to read that out loud exactly, but thank you, direct chat person. And there's only one. So if you just wrote in the direct chat, you know I'm talking to you. That's very nice. Cool. I mean, all right, sweet. I appreciate that. So basically someone's saying that this is also coming up in calc and that maybe the way it's coming up here might be even helping the way it's coming up in calc. And cool. And look, but also I'm also old enough to, so I totally appreciate that and put that in for, but also to all of you, also, I'm old enough to know at this point, like, of course, I'm always happy if I'm clarifying anything, but I also know one thing too. You know what really clarifies something? What really clarifies something more than anything is hearing it a million different ways from a million different perspectives. And it's the millionth way that will always make it sink in. So in other words, if those of you, if you were hearing this first from me, then it might even be a lot more clear when you hear it in your math class. It's just that you happen to often be hearing it in your math class first, which is because we have these prerequisites, which are so stupid. I mean, which I totally support. But no, honestly, everything and this is why, again, if I ever look to any of you as though I understand any of this, it is not because I'm smarter, and it is not because I worked harder, or I'm a better or anything. It's because I've done it so many freaking times, like really. And that's why it's best. The more times you practice and the more times you see this, nothing ever makes sense. I mean, really, like, well, that's a whole other discussion. But our whole education system is like built on so many like weird self-deceptions and lies. Like you can't learn something the first time you see it. The first time you see it is when you see what it is that you need to learn. Anyway, whatever. But thank you. I'm glad if this is clarifying what's going to be happening in math. So here's the thing, though. Here's my point, and then we will stop as soon as I hit that note. Okay, yes, my professor, he's in costume with using. What I'm saying is this vector here, let me just change view. This vector here, I say 5 meters at 30 degrees to the northeast is really equivalent to some amount east and some amount north. And that's true. That is totally true. And it's so true that it makes it seem obvious once I say it, maybe to some of you. But if you were doing this on your own, or if I were doing this on my own, and I had this, the same thing, right? There's 1,000 ways to break this up, most of which are dead wrong, and some of which are not technically wrong, but will really get you into trouble. So, I mean, for example, like, so there's a number. Well, actually, let me give a lot of ones that are wrong. Like what people will do if they don't practice this is you might do something like this. Some people will say things like, okay, I'll put, like they'll do like that, or they'll do like, or they won't even, a lot of people think, especially on exams, that this is just math. And they think the tips and the tails are just a technicality to make me happy, and they don't care about them, and they just start doing triangle stuff. Bad idea. It's not this, like you can't, two tips put together do not add to a hypotenuse. If you did that, and then you started tallying, and you might think, well, what's the difference? I'm still going to get the same triangle sides. If you did this first thing, then what you'd put in your chart, if you were following this correctly, you'd put a negative sign in for the y-axis, and then your whole answer is going to be wrong at the end. So it's not that. And it's not no tips at all. It's not that, but okay, or other things like that. But it's not like this or something. But now here's the one, it's none of those. And you might think, well, that's insane. I would never do that. But you would, or some of us would if we hadn't practiced it. I'm saying that northeast equals east plus north. But you might, here's the thing you might do that seems really reasonable. I'm even going to cross those out because those are all wrong. What you might do if you don't practice, because it actually seems reasonable, and actually technically it is right, it's just not good. What you might say is, okay, northeast equals north plus east. You might say something like this. You might say 30 degrees, 5 meters. You might say, sorry. You might say it equals north plus east. Okay, you see what I'm doing here? Like you might say northeast equals north plus east. Now, and technically you would be right. Like that is the same right triangle as I'm drawing. And a lot of people would draw it if they haven't practiced or thought this through. You might say that northeast equals north plus east. Is that a problem? Well, it's not strictly a problem, except for a couple of things. Number one, this angle here isn't 30 now, it's 60. Right? Or even let's say you really think that through, and then you're like, no, I knew that. I know that. I'm going to say that this angle is 30. Well, then if you do that, that's not 30 degrees northeast. That's 30 degrees east north. Like, honestly. Or put another way. So I wouldn't recommend that. I would recommend always, what I'm saying is, if you want a memorizer or a trick for doing these things, always draw the horizontal first, and then from the tip of the horizontal, draw the tail of the vertical. Like, honestly, literally, that it's not a law, but it is a trick that will never fail you. When you finally add all of the vectors together, and you got at the end of our whole big problem, and then we're going to be done. I'm just looking at the time. Okay, 9 minutes. At the end, when we got the numbers 4.4 and something. Hold on, let me just look at what numbers we got. We got 4.4 and 8.3, right? Or 8.3 and 4.4. At the end of the day, notice I drew 8.3 and then I went down 4.4. There's no law that says you couldn't do this. There's no law that says you couldn't draw 4.4 and then 8.3 like that. You could do that. But then, honestly, it's really confusing, because this is a right angle. You're going to get this hypotenuse, and you'll get that right. That'll be like 9.39 or whatever we said. But then then you have the question that confuses people all the time in SOHCAHTOA, which is the angle? Which is the angle I'm looking for? And they're both kind of confusing, because if you take this angle, then that's really east of south. It's not southeast, and your answer is going to be some number of degrees east-south, which is not the way anybody thinks. But if you take this angle, I don't know what that is, because then that's not what is that? That looks like it's north of east, but it shouldn't be north of east because it's pointing down. So I don't know. So what I'm saying is, what you'll notice, and you again, hopefully you're paying attention to me right now, but I never thought this through until I was actually practicing them on my own. When you get the final answer of what did I say? Of 8.3 and 4.4, whatever it was, the two final, 8.3 and 4.4. Notice then you've got choices of how to put those together in a triangle. I'm saying the thing to always follow, the thing to always do whenever you're making a triangle, when you're putting X and Y things together to make one big hypotenuse, always draw your horizontal first. So I went 8.3. Whoa, hello. So I go 8.3 to the east, and then from the tip of it, I go 4.4. I draw from the tip of it, I draw a tail, and I go 4.4 to the south. And then it's clear that the angle I want is the angle is the angle between the tails. So I'll even write that. The angle you seek is between the tails and from the horizontal. You'll know you've done everything as best as you like, in the best, most workable way. If in your final triangle that you get, if the angle that you're looking for is the angle that's between the tails, so it's like actually showing which way you're actually going, right? And not only is it between the tails, but it's literally measured from a horizontal as opposed to being measured from a vertical. So then your angle is clear. That angle, to me, once you get all this, that angle is clearly some sort of south of east angle. It's an angle that's showing me how much I've opened up to the south from the east. It's measuring how much south of east I am. If you do things right, if you always draw the horizontal first, and from its tip, draw the tail of the vertical, then things will all work out nicely and consistently. Again, I'm not saying that's not a physics law. That's a technique. That's like a teacher advice. But that's the deal with adding vectors by components. It's 124. I think that's actually all. And if I'm going to pause for a second. We've got 6 minutes, but I'm just going to pause to take a breath, and you look over for a second. Look over if that makes sense. Also, for a second, as long as we're here, we're still going to go a little bit early today, which is nice, or like a couple. We're certainly not going to go late. Look at that for a second and look over the memo that you just got about expectations about the exam. Just make sure you're clear about how the exam is going to work and how adding vectors works. Just pause for a second, just look and see if we have any questions. I'm just going to hang up for a second just to see if everything's clear. And then, like, if it is, we'll go. But let's just give ourselves, since we don't usually have this luxury. Oh yeah, in fact. Right, and this is what we said last. Okay. All right, I'm gonna. Does everybody, if you think you're clear on adding vectors, if you think you're clear on and you can still keep thinking, we still have a couple minutes, but if you think you're clear on most of the things, or you think you're okay, give me an electronic thumbs up or something, like, or electronic hand. Cool. Thank you, Caroline. Thank you, Caitlin. Thank you, Chloe. Thank you, Kevin. Thank you, Christina. Thank you, Savannah. Thank you for the, and there's okay, pause for 1 second. There's a good, thank you all of you, but pause for 1 second because there's a good question in the direct chat. You might not have thought of it. It might apply to you. Hold on, let me, there's a couple of questions in the direct chat. So hang on 1 second. Oh, great question. Okay. Wait. Okay, so someone in the direct chat is saying, are we allowed to write the midterm out on paper, take a picture and submit it online? Oh, for sure. Let me be really clear about that. Not only are you allowed, no, like, that's what I want. I mean, if we mean that's, yes, you should not try to type the midterm unless that's the way you've always been doing homework, or that's the way you're always comfortable doing math and science. No, you should write it out on separate. So any homework you ever did, whether it was on time or not, whether you got it back yet or not, those are all meant to be practice for this procedure, honestly, even just down to the, like, how to submit on Google Classroom. So yes. The exam is like one big homework assignment. It's like 3 big homework problems that just count more. So yes, please. Wait, hold on a second. Yeah. Oh, wait. No, and Caroline's right. But let me please, as long as we have this moment, and I'm not keeping you, this is super important. That's why we've been doing the homework the way we do it. Like, and the only difference is that this is more serious and more rigid. And I do want to repeat that. But oh, yeah. No. Okay. No. And thank you for qualifying direct chat person. Yeah. No, to everybody. Do I want your exam to be as neat and clear and, like, proud, dignified, presentable as possible? Oh, yes. Like, you want to make it as easy on me to follow and to see how much you understand and to see that you've taken pride in your work, and you want to make it clear that you didn't just, like, scratch it out, like, on the bus at the last minute, with a flashlight and toilet paper or something. Like, yes, I want it very nice, but no, this is problem solving. I expect that from most of us, definitely including me. You're still going to have an easier time making it nice and trusting it and thinking properly if you're writing out with pencil or a pen on paper. So for sure, no, you're taking out your own blank pieces of white paper. You're treating them like they're like a blue book. Like, honestly, to everybody, this is a very real good question. You take out blank, like printer paper or whatever, you treat it like it's a blue book. So you're writing everything out, writing with a pen or pencil. And I really encourage you to make drafts first. Honestly, the practice test is kind of just to force everybody to do a draft, even if they wouldn't. Like, you should be practicing it before you actually do the final copy. But your final copy, you write out on the white pieces of paper. And let's make this clear, just like with the homeworks, you don't copy and paste my questions. You don't do that. But you do label your answers so thoroughly, like it was a blue book. Like, you literally do, like, question 1, like, and then you write, like, here are the givens, here's the diagram, here's the question in my words. So your goal is so that I can grade your full exam. So yes, you don't type it unless, like, that's the way you're used, unless you like to do that. But And the more colors you can do, the better handwriting, the more diagrams, the better, blah, 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 blah. It's like a presentation. But your goal is to, on these white pieces of paper that are like a blue book, your goal is to present me with a document that I don't have to look at my own copy of the exam to grade your exam. That's a real thing. Like, I should be able to grade your exam. I should be able to be on a bus grading your exam, like without having to keep flipping back and forth to my original questions. You make the questions as clear as you can in your words. You show that you know the questions in your words. But right, okay, I'm dragging it out now. But right, you definitely don't have to type this. You definitely. Oh, and then like homework, you draw it out, and then and I know that the direct cap person gets me now, and I appreciate that. But then you scan them in, and just one last thing though, like homeworks, I expect it's going to be a multi-page document. I mean, it better be it better be a multi-page document. But please compile all those pages into one file, whether it's PDF or Google Docs or whatever, one file that then goes into the exam portal. And yeah, then you're just going to submit it in the exam portal. Once the exam comes out, it'll just look like a homework assignment, but it'll just be worth 100 points, and it'll be in the exam section of Google Classroom rather than the homework. And that's it. But yes, great question. Okay, sorry. Yeah. No, thank you. Yes, okay. And someone has to leave, and now it is time. Oh, it totally is time. I'm sorry. Yes, thank you. Great questions. Goodbye. Happy Halloween. Happy Halloween.
Happy Halloween. Have a good day, Professor.
Bye. Happy Halloween.
Thank you. You too.
Happy
Yeah.
Halloween, Professor. Have a great day.
You too. Thank you.
Professor?
Yes.
So I type all my homework.
Fine. Yeah, if you're comfortable doing that, that's fine. Just make sure. I mean, you should also put diagrams and stuff. But no, if you're good at that, I'm just saying you don't have to.
Okay. Thank you.
Thank you. Cool. Okay. Bye.